In this video, we're going to practice using reference frames, and we'll actually start out with 3 different reference frames. Let's see. Let's have the earth, the ground, and on the ground we'll put a house, and as you might imagine, that house is at rest relative to the ground. It's not moving. And let's also put over here, let's put Bob. Bob is at rest. Bob is at rest on the ground also, so he and the house are not moving relative to each other. And then let's have, let's have a bicycle. And it turns out it's a little bit tricky to draw bicycles, so I'm going to probably butcher this, but how about something like that? Oh my gosh. And there's a seat, and then on the seat we have somebody riding their bicycle. Okay, well, that's actually not terrible. We'll call that Alice. And then let's have one more object. And our third object will be a car. And our car will be driving to the right. And we'll just call it car. So we have Alice, car, and Bob. Now we'll give each of these velocities relative to the ground. So using our usual notation, we'll say the velocity of Bob relative to the ground is 0. And let's say that Alice is moving to the right, and that the velocity of Alice relative to the ground is, let's say, 5 miles per hour. Okay, but let's say the car is moving faster than that to the right. And we'll say V car relative to the ground is 20 miles per hour. Okay, now everything is one-dimensional. You can either move left or you can move right. You can't move up or down. We'll just keep things simple. And in fact, for the whole course for relativity, we're just going to consider one-dimensional motion, left-right motion. All right. So let's describe things from each of these people's points of view, right? So in Bob's frame, which is the same as the ground, Bob would say that Alice is moving to the right at 5 miles per hour, and the car is moving to the right at 20 miles per hour. So we'll start with Bob's frame here, and we can write that down. Bob's frame. It turns out that Bob's frame is the same as the ground frame because Bob's at rest relative to the ground, but he would say that V Alice relative to Bob is just the 5 miles per hour to the right, and V of the car relative to Bob is 20 miles per hour. Okay. So Bob's frame, the picture would be the same as the one that's already drawn. Now, how about Alice's frame? Okay. Well, put yourself in Alice's frame for a minute, right? You're on that bike. The car is moving to the right faster than Alice is moving on her bike to the right, right? So the car is getting further ahead of Alice as time goes on. So if you're in Alice's frame, if you're at rest on the bike, you would say the car is moving away from you, moving to the right, but it's not moving at 20 miles per hour. It's moving away from you slower than 20. It's moving away from you at 20 minus 5. So we would say, we could say that V of the car relative to Alice, right, is equal to V of the car relative to the ground plus V of the ground relative to Alice. Right? That's from the velocity addition formula that we derived in another video. Okay, well, V car ground, that's just the 20 miles per hour. And V ground relative to Alice, well, that's the same as minus V of Alice relative to the ground. Remember, if you switch indices, that's the same as putting in a minus sign. So we have this 20 miles per hour for the car, plus we have minus VAG. Well, VAG, we already know is 5 miles per hour, but we have minus VAG, so we're going to have minus 5 miles per hour. And so we have 15 miles per hour. So that's a positive number, meaning it's moving to the right. So Alice would say that the car is moving to the right at 15 miles per hour. And how about, what would Alice say Bob is doing? Right? So if we want to know velocity of Bob relative to Alice, well, that's velocity of Bob relative to the ground plus the velocity of the ground relative to Alice. Well, we know that Bob is not moving relative to the ground, so that's 0. And we know that the velocity of the ground relative to Alice is minus VAG, Alice relative to ground. We used that reciprocity already, flip the indices, flip the sign. So we already knew that that was minus 5 miles per hour. Okay, so we're kind of closing in on an answer here. From Alice's point of view, Alice says that the car is moving to the right at 15 miles per hour, and Alice says that Bob is moving to the left at 5 miles per hour. So this is 5 miles per hour to the left, and VCA of plus 15 is 15 miles per hour to the right. So this highlights the fact that a minus sign in a velocity is indicating leftward motion, whereas a plus sign in a velocity is indicating rightward motion. So we've studied things from Bob's frame and from Alice's frame. Next, we'll do it from the car's frame. So let's put ourselves in the car's frame. We know that Bob will be approaching the car from the right, and that Alice will be, the distance between the car and Alice will be growing with time, and Alice will appear to be kind of getting further and further away through the rear window, whereas Bob will appear to be coming closer and closer through the front windshield. Okay, so in both of those cases, from the car's point of view, Bob and Alice are both moving to the left, and we can write that out using the velocity addition formula. We'll start with Bob relative to the car. So we want to know what is the velocity of Bob relative to the car, and we know that that's the velocity of Bob relative to the ground plus the velocity of the ground relative to the car. But Bob is at rest relative to the ground, so that first term is 0. And we know that the velocity of the ground relative to the car is minus v of the car relative to the ground by reciprocity. And we know that the velocity of the car relative to the ground is plus 20. So here we'll have a minus 20. Okay, so again, from the car's perspective, Bob is moving to the left at 20 miles per hour. And you probably could have just seen that, right? We know that v car ground, which is the same as v car Bob, is 20. So if you flip those indices, v ground car or v Bob car will be minus 20. So that's sensible. And now we'll do the same, but for the velocity of Alice relative to the car. And we expect to get a negative number here because it's going to look like Alice is getting further and further away as seen through the rear window of the car. And so we should be able to find that by writing out the velocity addition formula. And if you're not clear on why I'm writing VAG plus VGC, remember I can get rid of the G's here. If our goal is to have the velocity of A relative to C, then I can always express that as two velocities added together. The first will have the first index, and then the second will have the second index last. And then I can put anything I want for these inner indices as long as they're the same thing as each other. So in this case, I would say, okay, I know the velocity of Alice relative to the ground. So I'm just going to use that term because I know a number for that. So I'm going to put a G here. But if I put a G there, I have to also put a G on the second velocity in order to keep consistent. So now I know what to do. VAG, the velocity of Alice relative to the ground, we were given that information. That's 5 miles per hour. And the velocity of the ground relative to the car, we were not given that number, but we were given minus that number, we know v car ground is 20, and therefore we know that v ground car is minus 20. And I kind of did a bit of a skip of a step there, and the step I skipped is that VGC is equal to minus VCG. When you swap indices, you swap the sign, and that's by what we've been calling reciprocity. Okay, so all that's left now, like we've done the physics, all we have to do is the algebra. We have 5 minus 20, which is minus 15 miles per hour. So from the point of view of the car, Alice is moving to the left at 15 miles per hour, and Bob is moving to the left at 20 miles per hour. So now we've expressed all of the motion of all of the objects as viewed from each of these 3 different reference frames.